theory, what is that?
So we're
Parts 1, 2, and 3.
that's right. Yeah. So ultimately we're going for this thing called Dirichlet's theorem, right? And the proof of Dirichlet's theorem is pretty involved. It's going to take us the last week to do the proof of Dirichlet's theorem.
So your class is going to run all the way up through 10th, right, or the 14th?
Yeah, I think so.
All right.
And
And your final exam is on Monday the 17th?
is that right?
I think the 14th we don't have classes.
Yeah, our last class is on Wednesday.
Oh, did I write that I'm actually having a class on
Is
this?
that right?
Yeah, I think we have Wednesdays, Tuesday,
Well, we'll go as so. Yeah, I guess that Friday is not. Can't have class actually. Right, I'm not allowed to have a class that presents new material. Of course, what people usually say is that this material is like 100 years old.
I mean, but just material that won't be on the final. So we could meet, but it wouldn't be on the final.
Right. Could say. Okay. 2-hour exam. Yeah, we could give a 3-hour exam. Generally I just give 2-hour exams. Stop it at 2.
Oh, usually that's only been 1 hour. Okay. Is it cumulative or is it just going to be the last? Yeah.
It'll be on the last. It's not going to be good. Yeah.
A little weird way that might not be.
Okay, let's get going. We were actually short of class, then there's no time to waste. Okay, so we're doing some basically elementary numbers here. In order to get to some actually advanced number theory, namely Dirichlet's theorem, right? And we finished up with this thing, Euclid's algorithm. Right, that says that if you have 2 integers and 1 is positive, then there exist unique integers with q and r such that a equals qb plus r, and r is non-negative and smaller than b. It's basically saying that long kind of concept of division with remainders works, which you did in elementary school work, but of course we don't present this in elementary school. Okay. So right, our ultimate goal is to get to this thing called the fundamental theorem of arithmetic. Right? So the fundamental theorem of arithmetic, which says that every if you have some natural number, then n can be expressed as a product of primes uniquely. N has a unique expression. Okay, and can be factored. Any number can be factored as a product of primes, where those primes are unique up to permutation. Okay, so and the Euclidean algorithm, Euclid's algorithm will be crucial in showing that. So just some basic definitions, which you are likely to be familiar with. So you have a and b, some integers. You say 1, if there exists an integer such that ac equals b, then we say a divides b. So if a can divide cleanly into b, we say that a divides b. Right? A is divisor of B. Right? So this we could explain to elementary school students. Right? If A is a factor, A is a factor of B. Right? A divides cleanly into B, we say A divides B. Two prime numbers, I assume you know what prime number is. Has no divisors. Right, so we generally only think of them as the natural numbers, right? And the number should be greater than 1, has no divisors, except 1 and itself. A lot of primes are. Here's an important notion, the greatest common divisor. So the greatest, this thing is the largest integer that divides both A and B. So the greatest is called the greatest common divisor. And last, if the greatest common divisor is 1, like there's no number excluding 1 that divides both guys, we say A and B are relatively prime. A and B are relatively prime. So for example, like 9 and 10. There's no number that divides both 9 and 10 cleanly except for number 1. So even though neither of these is prime, we call them relatively prime. Okay. And so we're heading towards the fundamental theorem of arithmetic. What will be useful is the following observation. If you have two whole numbers, then the greatest common divisor of A and B actually equals some multiple of A plus some multiple of B for some x and y and z. Okay. That is, you can reach the greatest common divisor by you want to think of it as being in the span of these two numbers. Okay. Where you're taking combinations where the coefficients are integer. You take integral combinations of these guys. The greatest common divisor is actually one of those guys. Okay. So here's the proof. Let's consider the span. Let S be the span, xa plus yb, x and y and z. But let's require that these guys are greater than 0, such that xa plus yb is positive. So we look at the span, but we're only looking at the positive numbers in the span. Okay. Let S, little s, be the minimum of this span. We claim that S is the GCD. Okay. So maybe the first thing. Notice that if some number any common divisor of A and B divides S. Right? If you divide A and you divide B, well, S is some combinations of A's and B's, right? So we'll divide S, right? So, that tells you that S is going to be bigger than the greatest common divisor, right? Because the greatest common divisor is going to divide S, so S is going to be bigger than it. Okay, so S is bigger than the greatest common divisor, and so it suffices to show that S is a divisor, is a common divisor, right? Because it's bigger than the greatest common divisor. If it's a divisor, it must be the greatest common divisor, right? Suffices to show that S is a common divisor, right? So that it will be the greatest. Okay, so here's how we do it. We're going to use Euclid's algorithm. Euclid's algorithm says that, well, we can write, let's show that, let's do this one first. Show that S actually divides A. Okay. So we use the Euclidean algorithm. We say, okay, we know that A can be recognized as QS plus R. We're hoping that R is 0, right? If R is 0, then we're done. Right, so this is 0, R is between 0 and S. Right? Okay, and then we think about this QS. QS, we know that S is equal to some XA plus QB, YB, or some X and Y and Z, right? Because it's in S, it's in capital S, right? So we write this thing, we say, well, QS is the same thing as QS is QSA plus QYB. Right? And so, what does that give you? That gives you that A minus R is QXA plus QYB. Right? And so, with R is 1 minus QAX plus negative QYB. Right? So we just substituted this thing in, right? We moved the R to the other side to get this, and then we see what R is. What's R? R is why did I write it this way? This should be X. Right. What's the point? R is going to be some combination of A's and B's. R is going to be in the span. Okay. Right, so R, notice that R was bigger than or equal to 0, right? So notice that, so then we see that, well, if we consider S minus R, right? S minus R is positive, right? S minus R is actually strictly greater than 0, right? And it's less than or equal to S, right? Because 0 was non-negative, right? Right? And so when we see, look, S minus R is then in capital S, right? S minus R is in S, right? Because R is of this form, right? S is also of that form. So it's the right form, and it's bigger than 0, right? And it's in the span, and it's bigger than 0, right? So, but S was supposed to be the smallest element in the set, so that means that S minus R must equal S. In other words, R is equal to 0. Right? S was minimal. The minimum of S. So S minus R equals S. R is equal to 0. And so S actually does divide A. And then you do the same thing to show that S divides B. And so we have that the greatest common denominator is some combination of A and B. And in fact, we know what it is. It is the smallest positive number you can get by taking integral combinations of A and B. And then there are a bunch of corollaries. Let's deal with some of them. Corollaries. If A and B natural numbers, A and B are relatively prime, if only that there's this x, y, and z, such that ax plus by equals 1. Right, so we've basically done half of that just now, right? In the forward direction, A and B relatively prime, then the GCD is 1. It's the same thing as saying that the GCD is 1. And we just saw that the GCD is expressible as some combination. Right? The GCD is in the span, so that tells us that we can reach 1. And then in the opposite direction, right? If there's this x, y such that ax plus by equals 1, well then any common divisor of A and B divides 1. Any common divisor of A and B divides 1. Well, that means that it must be 1. Right? It is right. Well, no, it means that it must be 1 or negative 1. It must be 1 or negative 1, and so the greatest common divisor will be 1. Wait.
You mean that shows that they're relatively prime?
Any common divisor divides 1, so it must be, so the only common divisors are 1 and negative 1. Right? In that case, the greatest common divisor is 1. That is to say, they're relatively prime. Corollary, another corollary, if A and C are relatively prime, and C divides AB, then C must divide B. Well, AC being relatively prime means that the GCD of A and C is 1. Right? In other words, that there exists x and y such that xa plus yc is equal to 1. Right? Okay. And that gives us an expression for b, x a b as well c b. And our question is, does C divide, we want to show that C divides B, right? So C and C divides YCB, of course, right? And C divides XAB, because C divides AB, right? So C divides B. Is that everyone okay with that? Not too exciting. Okay. You guys want to go to sleep and then wake up later. I'll wake you up in the next class. No. Anyway. Okay. So not too exciting, but I don't know. It's still sort of cool, I guess. Here's another corollary. If P is prime, and P divides A1, P divides some product, then P must divide some A sub I. If P divides the whole product, then P must divide one of the A sub I's. Right? And the proof is just to use the previous thing. Right? P is prime, so it's relatively prime to everything. Right? P divides this big product, so we break the product into this. Right? P divides this product, so it must divide one of these things. If it doesn't divide A1, then it must divide this. And then you repeat. Right? If it divides A1, then you're done. If it doesn't, then you say P divides A2, A3 through AR. Right? You say, well, does P divide A2? If so, we're done. If not, it must divide this. Right? Eventually, you get to the end, and at the very end, P must divide AR. Right? So if it doesn't get anything on the way, you'll have to divide the last time. So that's the that's the algorithm. Okay. So after all that boring stuff, we now prove the fundamental theorem of arithmetic. So fundamental theorem of arithmetic, which says that, of course, right, that if n is an integer, it is a whole number, then n has a unique factorization into primes. Okay. And the proof of this that the authors give is in my opinion, sort of hilarious. Okay. I don't know if it will strike you as funny, but something about this is sort of hilarious. So the first thing is, first we show that all n and n have prime factorizations. Okay. And the proof is by contradiction. You say, suppose there are guys who don't have prime factorizations. Suppose the set of integers, set of whole numbers without prime factorization. Suppose there is such a set. Suppose it's non-empty. Okay. And then take the smallest one. Let n be the smallest guy in there. Okay. It doesn't have factorization, it can't be prime, right? It's not prime, n is not prime, n is not prime. Right? Then that guy's not prime, and so n must be some product of guys. Right? Those guys are smaller, each of them being smaller than the smallest element in the set means that each of those guys must have a prime factorization. But then n has a prime factorization contradiction. Right? Since a and b are smaller than n, then a and b have prime factorizations. Right? But then you multiply those two things together and you get the prime factorization for n, which did not have prime factorization. So, contradiction. So does n contradiction. Okay. Part 2, showing uniqueness. So you say, well, let's suppose that n has a prime factorization and also has another prime factorization. Okay. You say, well, okay, well, I know that P1 divides n. P1, right? P1 divides n, so P1 divides this bottom thing. Well, that must mean that P1 divides one of these primes, right? P1 divides one of the q's. Let's say Q1. Okay. But then dividing Q1, which is a prime, means that it must equal Q1. Right? Because it's prime. Q1 has no factors other than 1 in itself. Right? So P1 is Q1. Right? And then you keep on going. P2 must divide these guys. And so you see that these things are equal, or of the same length, and they're just on the same thing. So this gives us the fundamental theorem of arithmetic. Any questions?
Is the reason that we get to start out understanding multiplication, but we have to use prove equal value for division, because we define the naturals as 0 and the successor of the naturals, and so addition and multiplication, natural and division is not.
Well, you're asking why we allow to multiply, but it's not.
Then we can divide.
Like, how do you know if you're given numbers, then how do you know that the product exists? That's what you're asking, right? Because we were showing that basically that a divisor, you have some right? So you're asking, how do you know that the product exists? I think if you actually want to do it, you can do it by induction. Yeah, that is, you'd have to induct, and so it goes to the inductive definition of the whole numbers. Yeah. Okay. If you look at so Fourier wrote something about this, and he approaches it by induction. as you see, it's not obvious that there will be such a cube. Right? You've got A, and you're trying to divide it by Q. You divide it by some number S, and you're trying to get this Q. How do you know that this Q exists? It's not obvious. Okay, so that gives us the fundamental theorem of arithmetic. This leads into as you know, we're ultimately trying to show this thing about Dirichlet's theorem, showing that in this particular sequence there's an infinite number of primes. Probably all of you have seen this proof, Euclid's proof of that there are infinitely many primes. Right? Who can somebody just tell me? I'm sure you know this for a while. What's the proof? Yeah.
Generally finitely many primes.
Suppose the finally
P1 to Pn.
Suppose there are finitely many primes, then you create some new number,
Which is the prime-ness of all primes plus 1.
P1 times P2 times Pn plus 1. Right?
That number must have a prime factorization.
Right. So n, you know that n has a prime factorization. Right. And it's q1, q2, s.
But n is not divisible by any primes.
Right. So, right, but take one of the primes here. Take one of the primes here. Let's say that it's p. Let's say that this guy is p sub I. Let's take one of the primes that divides it. Right? Pi should divide n. Right. But if pi divides n, then pi divides 1. Right? Because pi divides pi is one of those primes. Right? So it's going to divide this and going to divide this, so it'll divide the difference, which is 1. But that means that the prime is 1, which is not right. So p prime is 1, which is impossible. Okay. So So this is a famous old proof that people learn at the beginning of their mathematical education. But you see that it actually relies on the prime factorization, right? I think most people, when they learn it, don't think about the prime factorization. Rather think, well, look, this thing is if there are finitely many primes, then this thing is divisible. Then you create this thing, and then this guy is a prime, which is bigger than all the primes on the list. Well, but really, to do it right, you have to think about prime factorization. You have to have the fundamental theorem of arithmetic. In other words, you have to have Euclidean algebra. It actually is deeper than this. The book proves along the same lines this fact that the number of primes of the form 4k plus 3 is infinite. And since that's sort of along the same lines, I'm not going to do it. Okay? Instead, finally, let's do some more analysis. Okay. So, actually, this is not, we're not really going to do much analysis. At least we're not going to do all of actually to get to this thing called, our goal for right now is to get to this thing called the Euler product formula. Euler's product formula for the Riemann zeta function. Okay, so recall that s bigger than 1, we define the zeta function to be the sum of 1 over n to the s as n moves from 1 to infinity. Okay, so this is the celebrated Riemann zeta function. And Euler showed that actually this thing can be realized as an infinite product, 1 over 1 minus p, 1 minus 1 over p to the s. Okay, where p ranges over all primes. So all primes. Okay, so you can recognize the sum as actually, this infinite product of sums of geometric series, infinite product of sums of geometric series. Okay, okay, so that's our temporary goal before we get to the great proof of Euclid's theorem. Okay, so just to remind us, or define it, if you have some sequence, so here these guys, and 1, 2, 3, you have a bunch of numbers, a bunch of real numbers, you have this thing called the infinite product, and from 1 to infinity, it's just like the infinite sum. Okay, so what you do is you take the partial sums, right, partial products, like k from 1 to n, and let n go to infinity. Okay. So don't think of this as anything. It's not all that different. A creature from the infinite series, infinite product, infinite series. Okay, so here is the theorem that will be useful to us, right? You can think, like, if all of these a sub n's were 1, then this thing would converge, right? Okay, so basically you want to think of these a sub k's as something 1 plus some error. Okay, right? You want to think of this product. Right? When you're thinking about a sum, you think you want everything to get to 0. Right? Well, in this case, you're hoping that these differences from 1 shrink. Right? Because if they were all 0, then you have convergence. Right? So your question is to think about what condition do we need on these errors to make the product converge. Okay, so if we write a sub n as 1 plus little a sub n, it turns out that if the sum of these error guys converges, absolutely, then the infinite product of the a sub n converges. So absolute convergence of these guys is enough to guarantee convergence of the. This sort of convergence is enough to guarantee that the the infinite product converges. Okay, and to show this, those of you who are interested in this sort of thing, there is a very thick book by Conrad Knopf. It's called like infinite sequences and series. Knopf has like 5 little books on complex analysis, which are very nice if you want to be very condensed, simple, nice presentation of complex analysis that costs like $4 for each book. Then I recommend that. That's what I used in college, actually. We used in college. He also has this book, Infinite Sequence Series, where he talks about all the details of this. So we'll use the following lemma. to do it. So we use this lemma that, that the natural log of 1 plus x in absolute value is controlled by twice the absolute value of x if x is small. As long as we're close to 1, we have this different value. And I'm not going to prove it. This proof is basically just by power series. You take the power series expansion of this thing, and then you see that it works. Okay. So let's go back to the thing that we really care about, which is showing that absolute convergence of the errors forces convergence of the product. So you say, well, look, A sub n converges. So let's just assume that all of the A sub n are smaller than a half. Okay? Right? Because, you know, if for the guys who aren't smaller, there's only finitely many guys who aren't smaller than a half. Right? So let's just, you can hold those guys on the side and then just consider the rest. That's not going to affect the convergence to hold finitely. First finitely many guys, right? Convergence is determined by the behavior of the tail. Right? So let's just assume that all these guys are smaller than half. And then you say, well, look, if we look at the finite products, like the partial products, this is just e to the natural log. We rewrite this, right? We're not doing anything here, right? Absolutely nothing. We just wrote this as e to the natural log, right? And then we use the power, the property of the exponential function that I explained to my pre-calculus class not long ago, right? That the exponential product of these guys are just going to sum the exponents. Right? N equals n. Okay, so right now we have an expression. We have an expression for the partial products. Okay? And so let's look at this thing. Let's look at this exponent. You say, well, look, since all the A sub n's in absolute value are less than a half, we know that the absolute value of n plus 1 plus A sub n is less than 2 absolute values of A sub n by the lemma. Right? So that tells us that the sum that this infinite series, right, converges absolutely. Right? Because we know that the A sub n's converge absolutely. The sum of the A sub n's converge absolutely by assumption. Right? These guys converge, right, by comparison test. This thing converges absolutely, right, to some value t, right? Right? That is to say that the limit of these guys is some value b, right? And then you just use continuity. Apply continuity. The limit of the partial products is the limit of e to the sum. But by continuity, you can take the limit inside. Right? So you take the limit of this thing, which is b of t. Of e, yeah, continuity of the exponential function. Right? And so the limit So that's pretty cool, I think, right? That you look at the numbers, how they differ from one. Turns out that absolute convergence is enough to ensure the absolute convergence of these little error guys is enough to ensure product convergence into product. Okay, let me just add on one remark, which will be important when we get into the next lecture. Notice if a sub n is not equal to 1 to all n, then if we consider the product 1 over 1 minus a sub n, right, which should look, that's something we are interested in. Well, this is, of course, the limit of 1 over the partial product. Right. This is, if we look at this thing, right, which we're going to use in the Euler product formula, we see that this thing is the same thing as this thing, right? And by what we just saw, this thing converges, right? So if in addition all the a sub n is not equal to 1, then this thing converges. Also converges. Okay. So next time, Euler's product formula for the Riemann zeta function.